All right, it's 9 o'clock. My name is Seth Juarez. We're going to talk about deep learning with PyTorch, if that's okay. How many of you have used Python before? Okay. How many of you are C# programmers? Okay, everybody. How many of you are just thinking they're in the wrong room? It's okay. So just a little word of warning, like I go really fast. And so if we need like a safe word or something, where you're like, pineapple, and I like, okay, I'll slow down, just let me know. Because it gets super dodgy, like really quick. And so I want to make sure you understand. Because one of the things that I worry about is like, overall, you know, like AI has gotten really like bad, like we've done some horrible things with AI over the years that I don't want you to be worried about what we're doing, okay? And so if you feel like I'm going too fast or you want me to slow down, there's not so many of us that I could slow down. But I'm going to go really fast, and it's going to just whoosh, because I want to cover a lot of stuff, just so you get a sense for what's going on, because I feel like there's a lot of hype in this area, and once you know what it's actually doing, you're going to be like, that works? And the answer is yes, sometimes. And so we'll talk about that. All right, so let's talk about artificial intelligence and machine learning in general. AI, I think, is this big bubble. I don't know if that's the right term to use in the tech sense. So if AI is this big bubble, then machine learning lives right inside of it, right? And so sometimes I think people conflate these two things. It's not the same thing. For example, many of you could write a tic-tac-toe program without having to use machine learning, and it will always either draw or win, right? You can build one of those using standard search algorithms. But machine learning is actually a little bit different. And inside of machine learning, you have deep learning. Does that make sense? And so this is how I like to think about it. And so whenever people start to talk about this, they're usually selling something. If they're talking about this, they're usually making something. Okay, so be aware of that. If someone says they have advanced AI in their product and their marketing, it's probably a glorified database lookup. So be aware of that. Once you start learning the techniques of machine learning, though, you'll start to see that there's actually some cool stuff. Now, most of you are programmers, and if you're not, that's okay. Programming is basically this thing that we do where someone gives us a problem, and we come up with a series of steps to solve it, right? We call that an algorithm. And then we get some input, and then out comes the answers. But there's certain classes of problem that we've all dealt with, and you've all done this, where after like a couple of weeks, you have to add another if statement, right? You've all done this and gone home and taken a shower afterwards because you felt dirty. Or like you've changed like a 0.5 to a 0.7, and then it kind of worked after that. You know what I'm talking about. You've all done this. Don't look at me like you don't know what I'm talking about. We've all written stuff like that. Because it turns out that those kinds of algorithms that we've written feel a little bit squishy, right? For example, if you were given a picture of a number and you had to tell us what it is, like you feel like all the if statements in there, and there's like weird for loops, and there's like 0.5s and 0.7s. Those kind of problems, when you get that hoarse sense of like this feels a little squishy, that's where machine learning might work, because machine learning, instead of writing a series of steps or an algorithm, we actually swap this, and then that's how it works. Okay? Think of it like that. And the output of machine learning is an algorithm, but it doesn't look like an algorithm that you or I are used to. But output is a file. It's basically a file with stuff in it, and you can use that in a program. And in fact, I'll show you at the beginning what we're going to build so you can see how it works. Okay? In data science, we call this a data, and the thing is called a model, right? You've heard of an AI model or a machine learning model. This is basically an algorithm. And you give it stuff like this. By the way, we're going to use PyTorch in this case to build it. And sorry, I went too fast. You're going to give it data. We're going to build a model algorithm, and then we're going to use that with new input to produce answers. That's what this is all about. Okay? If anyone makes it more complicated than this, just let them talk. But basically what's happening is we're making a model or an algorithm that later we can use to make predictions. Okay? And in this case, we're going to do this number thing. And the reason why we're going to do this number thing is if you've probably all seen this, it's because I don't want the problem to be the focus. I want the what we're building to be the focus. And I want you to know what is actually happening inside of these things, okay? Because I feel like there's way too much going on. All right, are we good so far? It's not dodgy yet. Okay. Basically, we want to build this, right? I don't know what language this is, but you've all seen something like this. You want a function that says get digit, and you give it a picture and a number comes out, right, between 0 and 9. That's what we want to build. All right, so how do we do that? Before we do that, let me say that machine learning is basically like building any function that, given an input, produces an output, right? Because that's what algorithm is. But the question is, for machine learning, does the x look like? And then what does the function look like, right? Because that's like this is easy, right? Because if you have pictures, it's basically a bunch of pixel numbers, right? But this is a little bit more questionable. So what I'm going to do is, instead of talking about numbers, I'm going to level down one more time so we can get some intuition, and we're going to talk about this problem called the 9 squares problem. So imagine you had write an algorithm that, given a picture of 9 pixels, grayscale, you get 9 numbers between 0 and 255, you need to predict whether it's darker at the top or darker at the bottom. That's easy, right? Your input is something like this, right? For the first picture over there, like you have 182, 199, those are the intensities, right? Now, for those of you that want to be pedantic, I know that 255 is white and 0 is black, but I switched the colors around so that the slides would look nicer. Okay? So I know this. So here we go. These are the 9 pixels, and then this says that it's darker at the top. Okay? Do you see that? It's pretty easy. So how would you, as a programmer, now you can turn your programmer lizard brains on. We all have them. We try to optimize everything. Like even when I'm typing things, like if there's a word that ends with a T and the next one starts with a T, for some reason I don't type the second one, because that's what we do. Programmer lizard brains, right? So how would you, as a programmer, write an algorithm that tells you if it's darker at the top or darker at the bottom? Bring it. I will repeat it for the recording. Yes? What? So now you just want to know this row and this row. We don't even care about the middle row. So you're saying add these all up, divide by 3. Add these all up, divide by 3, and then see which one's greater? Is that what you're saying? How about we take out the divide by 3, because it doesn't matter? Okay, you did it, right? Super easy. Add the top 3, add the bottom 3, whichever one's greater. That's it, right? That's really stupid, but you're all okay with that. Okay, now I'm going to force you to put it into very specific structure, okay? And you're going to have to think a little bit more on how you would do that. So this is the structure that I'm going to use. And what I want to do is I want to pick a series of W's such that when I multiply each of the pixel numbers coming in and then add them all together, it gives me an answer. So what W's would you use, already understanding that we're just going to add the top 3 and add the bottom 3 and see which one's greater? What would you do? Again, we don't care what's in the middle. What W's? Yes, sir. What W's would you choose? 1, 1, 1. 0, 0, 0. Minus 1, minus 1, minus 1. That's super clever, right? Because when you take the first 3 pixels, multiply them by 1s, and add them, you get the positive side, right? When you take these, we don't care about, so we zero it out. When we take these 3 pixels, multiply them by minus 1, and add them together, we get minus something. And these two fight each other in such a way that if it's more negative, it's darker at the bottom. If it's more positive, it's darker at the top. Right? Duh. Any questions about this so far? That was a trick question. You're supposed to ask about the B. Nobody? No? Oh, there you go. What's the B? Great question. Well, what if you want to make an algorithm that says if it's only slightly darker at the bottom, or a little less darker at the bottom, but within a specific range, then we want to guess the bottom? Well, then what you would do is you would add a negative B, like a negative something, right? Because this would bias it towards the bottom. Do you see that? If you add a positive number, it would bias the prediction towards the top. Okay? We have a very, and for those that want to know, in data science, we have a very specific term for this B. It's called the bias. That's what it's called. Because it lets us bias towards negative or positive. Okay. We okay with this? Let's test it out. So I got to get closer because my clicker doesn't like it. Oh, went too far. So just another way to look at this, by the way, is we take all the x's and the w's, we multiply them, and then we get this, and then we add them together. Does anyone know what this is called in maths? By the way, here you have maths. In America, we only have one. So I don't know what the extra one is that you have yet. This is called the dot product. Okay? And let's test it out. So we put some ones in there, and we put some minus ones. This comes out 236, so then the answer is darker at the top. Same thing with the bottom one. Negative number, darker at the bottom. Super easy, right? So basically, what you just divined is a machine learning model. You give it a picture, you learn this magic W, you multiply it, dot product here, add the bias, and then if it's positive, you guess top, negative, you guess bottom. That W is actually the model, and that's prediction. Like if I had a mic, I would like drop it. That's it. Like what you just learned is the foundation of all deep learning algorithms. Right? Isn't it? And you're like, wait, does that work? By the way, those that are data scientists here, am I right? That's why when it's AI, it's hype. When it's machine learning, it's engineering. This is what it is. And you might be thinking, well, how do we get all those W's and B's then, right? Let's just say we have a generic problem that we don't know. We had to guess them, right? But what if you want to like get the W's and B's yourself? Let's just say you have another problem and there's like 1 million pixels, right? How do you find these W's and B's? Well, the best way to think about it is like this. We want to find something, W's and B's, that minimize the amount of mistakes that we make when we're doing this, okay? So what I'm going to do is now is going to get a little dodgy. And so remember the safe word. If you just say it out loud if you want me to slow down or it doesn't make sense, because I want you to understand what's happening, okay? So we're going to make this function, if that's okay. And let me tell you what this function does. And right away, you're going to see it. So n is the number of example of 9 square pixels, right? We'll say we have 1,000 of them. What we want to do is this y represents the right answer, top or bottom. Okay? This is our prediction. Right? Let's just say top is 1 and bottom is 0. If we guess 1 and the answer is 1, what does this equal? 0. If we guess 0 and the answer is 0, what does this equal? Right? It's good. If we guess wrong, this equals something other than 0, right? So we want to find a formulation of this thing that we have in such a way that we make all of this 0. How do we do that? Well, that's a good question. Notice that I'm going to fudge this a little bit because we have a squared over here. So we're just going to take this all away and look at this one function called x squared. Do you remember that? What does that x squared look like if you were to draw it? I'll give you a hint. Do you remember this? We learned this like in primary school, right? Or maybe later. What's primary school for us? Is that like grade school for us? I don't know. Oh, what's that? Okay, so we learned this in primary school then? Well, you might learn it earlier because obviously you have more math than we do. So this is easy, right? Because x squared at 0 is 0, right? X squared at 3 is like 9. X squared at minus 3 is 9. And what we want to do is we want to find a configuration such that this thing in total equals 0, right? Because that's what we wanted to do. Remember the function before? We want this to be 0. So let's just pretend all of this is in there. We want to find a configuration such that this equals 0. Well, where does this equal 0? Give you a hint. It rhymes with hero. 0, right? But let's pretend you're Mario from Mario Brothers, but the 84, 85 version, right? And you're just standing right here at x equals 3. And you don't know, and you're blind Mario. Like, what do you do to get to 0 when you're playing Mario? Well, you push down because then he slides on his butt, right? And then it goes down. But how do you know which direction to go in? So just pretend you're standing there at x equals 3, right? What you do is you want to go down. So if you were blind, what would you do? Think physically. Would you put your toe a little bit forward, right, and see what's going on? And then you'd put your toe a little bit back, see what's going on, and then you'd have this little thing, right? And that would tell you the slope, right? So we'll take a little bit of the y direction and a little bit of the x direction and divide them and then come up with the slope, right? And that little thing will tell us which way to go. We'll call this dy by dx. And then we'll be even cleverer when we make these things go to 0, right? And then that tells us the slope at this point. Congratulations, that's all of calculus. Well, half of it. It's called a derivative. The down button on any function in maths is a derivative. It tells you which way things go. Does anyone know the derivative of x squared? That's right. And the way I think of this, because I'm kind of dumb, is when anything's in the exponent, like when you take the derivative, they graduate to the front, but because they miss them so much, they take one off. That's how I think of it, because I'm literally 5 years old in my head. So 2x. So let's do a little test, okay? You ready? So we're at x equals 3. What's the value of the function? 9. What is the value of the derivative at x equals 3? 6. Okay. So which way do we want to go? Do we want to go in the negative direction or the positive direction to get to the 0? Negative direction. So we'll subtract off the value of the derivative, okay? So we're at 3, right? And we want to subtract off 6. Okay, so where does that put us? So we'll go 6 over. So 3 minus 6 is minus 3. Okay. That's a problem. We got to do this again. So what's x squared at minus 3? 9. What is the derivative at minus 3? Minus 6. So what we're going to do is we're going to say minus 3 minus a minus 6. And as you know in math, there's no subtraction. There's only addition of negative numbers. So the two things cancel out, and we get minus 3 plus 6, which puts us at... Do you see the problem here? It's going to happen forever. In fact, if you were to start at 4, you would bounce out. So what do we have to do? Well, we have to take a fraction of the value of the derivative and then take the step. That thing in machine learning is called the learning rate, and what you've just learned is gradient descent. If you want to be pedantic, the symbol is like this. Okay? So basically that function that I showed you at the beginning is called the mean squared error loss function. It tells you how bad your choice of W's and B's are. And what you do is you take the gradient of that function and you subtract off a scaled bit on the W, and you do this until it stops changing. And it's a for loop. Do you see how it got dodgy like really quickly? Everyone was okay up until I did this slide right. I was like, I got this, and then it went here. But don't despair. Basically what we're doing is because this cost function that we built on top of the model function, right? They're related to each other. This cost function lets us choose the W's and B's that best represent the answer to what we're doing. But we've chosen a structure or a model first, and then we've chosen a way to optimize it. It's called gradient descent. Are we okay? I didn't hear pineapple. That was our safe word. Okay. How am I doing on time? Okay, good. Perfect. By the way, this is what this looks like, and this is what this looks like, if you're wondering. Everyone okay with this? Turns out it's wrong. I forgot a 2 over here. Sorry about that for the one dude or gal that was doing all the maths. Forgot a 2. Okay. So now, that's good. We okay with that? So now we found a formulation of this. Now here's another question. What if we wanted to guess the top, the middle, or the bottom? Do you see that? Like, what do we do for that? Because remember we had that little one structure that divided things up for us, and we just had a W and a B, and it told us plus or minus. What do we do for this case? Well, we just make 3 of them. And then it turns out to be something like this. For those of you that are looking at this is a linear algebra, but when I look at these kinds of dot products, I think of the Cookie Monster because, again, I'm like 5 years old in my head. So I take this thing out, I turn it over, and I go, num, num, num. So it's like 3 dot products. So num, num, num. You don't have Cookie Monster here? You guys, what kind of childhood do you have? Is there a Cookie Monster in the UK? They're like, I don't know what it is. Does anyone know what the Cookie Monster is? The one dude over there, the math guy. Gosh, well, I know how we made up for not having all that math. We have the Cookie Monster. So you take this and you dot product. Look what this does, though. This zeroes out everything except for the top 3, right? When you add them together, it comes over here. If you do the second one over here, the second num, it zeroes out these ones, and then it adds the middle 3. Do you see that? It's pretty cool. And then when you do that on the third, it comes out. And so now you just pick the max index. And then you're done. Same thing. All right. And this, again, is also a model. And you just predict the one that's the greatest. Are we okay so far? Okay. All right. So let me show you what's going on and why PyTorch is actually really cool. So you've noticed that if you're looking at machine learning in particular, that you need to have blocks of numbers all over the place, right? You have to have they're called matrices, right? And you have that everywhere. And so in here, you can see, is this big enough, by the way? There you go. Okay, so what I'm going to do is I'm going to show you like what PyTorch does. So I just made a random 3x3, picture thing. Do you see that? You can also do like another random thing. You can notice that it's pretty easy to just make these things. Now, you can also add things together. But in PyTorch, like for example, if I were to say x add y or plus y, you'll see that this tensor comes out. When there's a little underscore, this little thing in PyTorch says replace what's in here, right? Because it turns out the interesting bit, and you'll see this in a little bit, is that these things get to be pretty big. These tensors. So, for example, here we're going to make our 9 square things, right? And this is the interesting bit because the first tensor we had was 3x3, but now we have a 3x3, but we have 400 of them. So now you have this matrix that's 3-dimensional. We okay? I told you to get dodgy fast. So these are our 9-pixel things that we're going to start to do experiments with. But now we have 400 of them, so now we have a tensor or matrix that's in 3 dimensions. We okay with that? Like think of this, like a regular picture is, let's just say it's RGB picture, is a 3-dimensional tensor. Because for every point pixel, you have 3 numbers, right? And so it's like having 3 matrices on top of each other. Now consider the case of video. Now you have a 4-dimensional tensor, right? Because for every slice, you have RGB plus you have this over time, right? Which is, now you're starting to think, oh, this is why we need tensors, right? Because we need to store the stuff in there. And PyTorch is really good about storing these kinds of things. But just to show you that it's actually a good thing. By the way, I can also do this, like I can view into it. So now instead of like having it all, because remember how I had it on one row before? Now I just do a little bit of a view and I have 400 over 9. And just to show you that this actually generates the right thing, what I'm going to do is I'm going to generate the tensors and I'm going to draw them out so you can see them. Give it a second. But basically all those things that I just built made this. Now, by the way, this is all available on GitHub, and so if you're stressed out that you're never going to see this ever in your life again, you may not, but you have the opportunity to if you wish, right? Notice that in this case, I built this one and it's darker in the middle. And if I were to run this all over because it was random, it will do it differently every time. Okay? So that's what tensors are for. You can see that there's a lot of other tensor beautiful things I did. For example, notice that here, I wanted to generate the actual right answer. So I built the magic W that we know is the right one. And then I said X matrix multiply times the magic W transpose, which means that it did the Cookie Monster num 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 over all of those examples to produce the right answer for me. Right? And then I made it a little nicer, by taking the argmax, and this says this one, the middle one is the darkest, middle one darkest, middle one darkest, because there's 400 of them. And then what I did is I transferred them over to look like this, so they would be vectors. And you can see, once you start playing with tensors, you can start to it's like Play-Doh. You can start to do stuff with it, and oh, I want it to look like this, and that's what you do. But again, you always start from the raw materials, which are, in this case, I like computer vision. And so when you're working with pictures, you're going to have a 3D tensor that has a picture. For every pixel, you're going to have 3 numbers, right? Then what you can do is you can make it grayscale by flattening, and then you can string it out if you want. You can do all sorts of other things. So that's tensors. Oh, by the way, this is what I'm going to cover. And I forgot to mention that I'm going to use Jupyter notebooks, which is a really nice thing. Jupyter is really easy to install, and it lets you, you see how I was hitting enter and it was showing you stuff, and I can change stuff around. It's really nice to experiment. So that's what I was using. So tensors. Any questions about tensors? It's the foundational block to all deep learning things, because it doesn't matter what you're doing, you got to put it into a vector of numbers. That includes anything that's text, that includes anything in your database that you want to do machine learning. It has to be converted into a tensor so that deep learning can happen. Okay, so that's what we just did. Super easy. But the thing about tensors is they're kind of special in PyTorch, because many of you that have done this before, there's something called NumPy that has all of these things in there too. But for this, it's a little bit easy. It's a little bit better, because here's an example. So here is, you can see right here, I just made a new tensor that has some numbers in it, and I'm going to say that it's darker at the top. Okay, and now what I'm going to do is I'm going to create these new tensors for W and B, right? Because remember, we're going to create this function that's going to learn what those W's and B's are on its own, right? We already know what we think they are, but it's going to learn something that will always work. Okay, but here is the bit that's interesting, right? And here is the part that I want you to be aware of. Do you remember that, we don't want to calculate derivatives and code them in, and so these tensors, what they will do is if you say, I need to have the gradient or the derivative with respect to this variable for whatever you use it for, it will store it for you. How does it know to do that, though? Right? And that's the part that I think is super interesting. So what I'm going to do is I am going to make the h function. And is this big enough, by the way? Okay. So this is the prediction function, and this is the loss function. Do you remember that? We wrote that up ourselves. So this is, we take the W, we do the Cookie Monster operation with X, and then we add the bias. This is our function. This thing here is the loss, right? Remember, if we get the right answer, then that means this is 0, and the mean is, we want this to be 0, okay? So now the question is, how does it know to calculate the gradient of this function with respect to these variables? And this is where PyTorch is super cool, right? Oh, by the way, let me show you what I mean by this. So I'm gonna run this, and you're gonna see, for example, that I can say loss, and I can take the grad function of this, and you're going to see that it knows about, the gradient of this. Here, let me zoom in because I see people looking. This is the function, because if you think about when you execute this loss, it's going to produce a value, which is a tensor. How does it know how it arrived to this value? Well, it knows that there was a mean that happened, right? And here's the other bit, because if you think about derivatives, it's really interesting. The derivative of any function is the derivative of the outermost function times the derivative of the inner thing. And you keep doing this all the way down, right? So here's another interesting thing. I can say something like, what are the other functions that generated this? Do you see this? Oh, whoops. This is power, represents that thing. You see how it starts to like dive into that? Now if I were to go into the 0 element and then 0 again, you're going to see that it's this one, and then I could even say, well, what generated you? Oops, I spelt it wrong. Looks like the next thing we did is we did a subtraction. And so when you look at this entire operation, when it comes to like storing this stuff, you can see that this is basically what is going on. I need a control minus there so you can see it. This is basically what's happening to this operation. And you can see right up here, the mean is the top level thing, then we're squaring it, then we're subtracting, right, some constant, y, minus something that we added together, which was a matrix multiply of a constant, which is x, times these two variables, w, and then we add b. Do you see that? And the reason why this is important is because if you're trying to compute the gradients with respect to w and with respect to b, it depends on all the operations that flowed to it, right? And so it will go ahead and as you put these variables in, like it will flow up, forward, to compute everything, and then to compute the gradients, it will flow backward. This is why it's called backpropagation. Right? It's super cool. And now, because I don't have to do anything, I basically have to say I want to have the gradient of this one computed and the gradient of that too. Then what you can do is then you can use these functions to generate the gradients of the tensors that you want and then subtract off in a for loop and run it over and over again. That's why they're kind of special. Okay? That's why tensors are special. And that's why you wouldn't just use NumPy, for example, if those of you that are Python users, because in PyTorch you actually get to like keep all the gradients of the tensors as you go along in the operations, which is really cool. And this is what you saw, right? Which is really nice. And many of you that use TensorFlow have seen graphs like this because they basically do the same kind of thing, but their graphs are required to be static. Right? You have to create those graphs a priori and then optimize them. In PyTorch, you can go as you like because notice that as you run it, it's computed dynamically, like what function, what's the gradient function for this? Well, it's that one, right? And well, what created that one? Well, that one and that one. You can see all of that going on. Okay. Questions? Okay, now here's the next bit about PyTorch that's really cool. Oh, good, I have all sorts of time. I was getting really nervous. The first thing is we need to find a way to represent an individual thing or a set of things. And for us, we want to represent like a set of the 9 square things, right? So let me show you what that looks like in PyTorch, which is really nice. So the base class for a data set is this. And this is why I like PyTorch, because like it feels like a programmer wrote this. For those of you that are not familiar with the syntax of Python, this is basically declaring a class called Dataset, which is supposed to be the base class of all other data sets that you use inside of PyTorch. It has a couple of things. The first, there are just 2 that you really need to implement. The first is, give me an item at index foo, right? So give me the 15th 9 square pair, and that would be an x and a y pair. This is the other thing you need to implement, which says how many of them are there. That's it. That's really cool, because now when I want to do my 9 square thing, I basically just need to define something like this. Now, if for those of you that I am cheating, right, and basically what you want to do with a real life data set is get like a picture of a cat and say have an X that's a cat and a Y that says this is a cat. But basically what I did is I generated all of this data myself, and I tell it, how many do you want? Well, I'm going to create these many, and I'm going to generate these things, right? And instead of doing it but 3 by 3, I just have the 9, so it's all flat. And you can see that just like I did before, I generate the y's, which are going to be a vector of size 3, and it's called a one-hot encoding, which means you have, like, for example, top, middle, bottom. There's going to be 3 slots. If the answer is top, you put a 1, 0, 0. If the answer is middle, you put 0, 1, 0. And if the answer is bottom, you put 0, 0, 1. Okay? And so that's what this generates. And so now, on the constructor side, when I want to get an item, I just, like, return the thing. And if I want to get the length, I just return the size. For those of you that aren't familiar with Python, hopefully there's enough in here that you're like, I see what this is. It's basically an object that represents all of the 9 squares you're going to use for training. Yes. The cool thing is, like, for example, if you're working with terabytes of data, of picture data, what you can do is you can store that, for example, in our cloud, we have a machine learning service that allows you to mount Azure storage as if it was a hard drive. And then what you can do is you can load this up and say, have a file that says, oh, there's 10 million pictures in there. And then you pass the file in. You say, oh, there's 10 million pictures. But you only get them when you need them. Right? And so this is a really nice way to loop through all this stuff. Okay, the next bit of thing that's important, here, let me show you that this actually works. So here are a couple, I loaded 256 of them. You can see that it just basically prints the things out, which is really nice. And now there's this next thing called a data loader. Now, when you're working in this loop of things, instead of giving it one example at a time to optimize, you know how Mario needs to take steps towards the 0, but he needs to explore the space? Each one of these examples gives you where he is, right? The data loader lets you load up a number of them at a time so that he can actually explore 100 at a time. Because, for example, you can't give it all of the, if you have 2 terabytes of data, you can't give it 2 terabytes of pictures and have it optimize the thing. It's just not feasible. So instead we take chunks of the data called the batch size, and then you can do that. Now the data loader is really nice because what it will do is it will, if I say a batch size of 5, you can see that it will load 5 of them. And then you can work on those. We okay? Hopefully it'll start to come together at the end for those of you that are having a hard time. Okay, so we did that and we did that. The next bit of thing is this notion of a model and a loss and a cost function. I already showed you what those were. But let me show you that because these things happen so often, right? For us, you can see that the model function is this one right here, and the loss function is this one right here. But these things are so common that they basically, in PyTorch, created a class to represent these things, right? The first one is called a linear model. The first one is called this thing called linear. And the second thing is this thing called the MSE loss. So that's basically the 2 things. You can see in this case, you can use this as a substitute for the actual y equals W transpose X, H of X equals W transpose X plus B. You can substitute that. And for our loss function, we can just do this. Because it's it happens so often that there's a class for this. Now, here's another question that you might have. But Seth, why did you make this class then? Well, because it makes it all into one nice function. Because PyTorch is really nice because when you're creating models, you can inherit from this thing called module, and then you can initialize it, and then you define this thing called a forward operation, and it will compute the backward operation for you. Because as you might suspect, we're going to start to stack these things. And so this is an exact way to replicate the other thing that we just built. Okay? And you can see that there. Now I added a little function there at the end which makes it sum to 1, which makes it look like a probability. Okay? I just want to let you know that that's what's happening. That's all that's doing. I just added another function. Now, so in PyTorch there's a ton of these kinds of things, these little helper things, so you don't have to write y or W transpose X plus B a million times. This will do it for you. And there's a ton of different loss or cost functions that work mathematically better depending on what's going on. Okay. Any questions about that? By the way, if you want to see what this actually looks like, you can see that it's basically similar to the thing we had before. But now, instead of having the W transpose X plus B, this is all like contained in this little bit right here. It has the variable W and then the variable B. Well, I guess this is W transpose X plus B. It puts it into like one operation, right? So now because we have these cool ways in programming to like put stuff together, instead of having to keep the derivatives in separate places, it puts it all in one place, which is really nice. Are we okay? No one said pineapple yet. I'm going really fast. They're recording it. You can watch this later. Okay. All right. Good. All right, so that is a way of now not like the basic thing. We're, again, still working on exactly the 9-square problem, but I'm putting it into PyTorch isms for you, okay? All right, so let's talk about, well, how do we optimize the thing now? And here is the bit where PyTorch really, really shines. So let me go back to this thing, and let's look at this squares problem, okay? So what I've done is I've created this thing called a linear model. I actually imported the squares data set that I had before. So you can see that's right there. And you can see that I just printed out the first couple, so you can see they're all coming out. Now the first thing that's interesting, and I did not mention, is this little bit of goodness too. And I totally forgot to mention this. With PyTorch, you can actually, because we're doing a lot of matrix stuff, basically we have used GPUs forever to do a lot of matrix stuff so we can like play games. But it turns out that it's also really good for stuff like this. So one of the things that you can do is you can check if CUDA is available. And CUDA is like an NVIDIA library that lets you like push everything over into a GPU. And so everything I've showed you, which is really nice, can actually also run on a GPU. So I check if CUDA is available. You can see it's true. And then I just say, okay, if CUDA is available, the device we're going to use is CUDA. Otherwise, we're going to use something else. In this case, it's the CPU. So now what we're going to do is we are going to define our model function here. That's our linear model. And then here, I'm just going to say, hey, by the way, run it on the device, which for me is going to be GPU. In this case, I'm using a different cost function, right? Remember, it was a mean squared error. It turns out this is better. It's called binary cross entropy loss, for those that are wondering. And it's better at doing loss when there's like you have to guess between 3 things, right? Mean squared error is good when you have to guess between 2 things, right? And you're probably wondering, like, how do you know this? Well, you use data science. And science, as you know, is glorified guess and check, basically. Remember, we have this thing called the learning rate. I'm setting it to this tiny thing. Now, you're probably, for the optimizer, I'm going to use this thing right here. You're probably wondering, well, Seth, what happened to gradient descent? Gradient descent is I could have used gradient descent here, but I chose Atom, which is a smarter gradient descent. Because what gradient descent does is it swings wildly all over the place. The Atom optimizer will be smart, like it can tell about momentum, and so it'll like, you know what I'm saying? Instead of like going all over the place to find that it's a little bit nicer about finding its way to the optimum, so I'm going to use that. Then I'm going to use a data loader for batch at 128, and then now here comes the loop. And this is the bit that I think is absolutely brilliant, right? Because of the way PyTorch works, right? By the way, this is, remember how we had this batch loader? It will tell me what batch I'm on, and then it'll give me X and Y from the data set, because the data loader, remember, loads them up for us. What we have to do is we have to zero this out. And the reason why is that gradients are cumulative, right? You might run a number of operations, and so it needs to, so for every, we're like, okay, zero out the gradient so we can start again. The first thing we're going to do is we're going to run the model on X. And it's going to give us a prediction. You see that? Then we're going to see, okay, how good is our prediction? Or our cost function? Now, this is the beautiful part. Once you've gone forward in the operation, you can say, go backward to flow the gradients down. And remember, there was another step that I kept like not showing you. We have to have a W, and then we have to subtract off a scaled fraction of W minus, you know, the gradient. The optimizer.step will do this for all of your tensors that require optimization. So for us, in this case, it'll be both the W and the B. So it will subtract this off. So as you look at this, like everything I told you before was true, right? We're going to zero out the gradients. This is like a little bit of housework, right? Because we need to make sure that everything's kosher. We're going to do our prediction. We're going to see how bad it is. We're going to take the gradients, and then we're going to update all of the variables using the, remember, W colon equals W minus the alpha learning rate times the gradient with respect to that value. This does it for the W and the B. And then it runs. Okay, so you can see that the error function goes down, which is what we want. Is it 0? No, that's okay. And then these are the W's and B's that it learned. By the way, one thing I also did that I did not tell you is I divided everything by 255 so that the input space is between 0 and 1 instead of 0 and 255. Right? It makes it more numerically stable. So here is the loss function. Is the loss getting better? We want this to be 0. Is it 0? No, but is it going towards 0? Yes. So should I have kept running it until it got to 0? That's a good question. But it depends, right? And so the answer to all of the questions is you just need to use a little bit of science. All right? In this case, let me show you what it learned for its W's and its B's. Did it find that magic 1, 0? Like, remember the matrix was supposed to be 1, 1, 1, all zeros, 0, 0, 0, 1, 1, 1. Did it learn that? Did it learn something that would work, though? Yes. It turns out that all of the first things are going to be positive, and so that's going to be, it's going to negative everything else out. Same thing here. These three, positive, negative everything else out. So numerically, it found something useful, right? All right, so let's use the model to do a little bit of prediction here. So I'm going to take this thing right here. You can see that when I'm running this is for me trying out the model, right? This is the image I'm going to use to predict, right? Notice that it's definitely darker at the top. What I do is I run the model on a new tensor that I just built. This reshapes it in a nice way. And then I say run it on the device that we want, divided by 255. So this is basically taking this and putting it into the model. And then it prints out what it thinks it sees. And you can see that it definitely thinks it's darker at the top. Let me do something interesting so you can see, because right now many of you will be tempted to think that those are probabilities. Let me do 128. Let me do here 123. Do you see how it's still guessing the right thing? Let me do 233. Okay, so look at this here, and this is interesting, right? When you remember how I said I used like a softmax? This is supposed to equal 1 when you add them all together. Right now it thinks it's 15% the top versus 84% the bottom. Is this really the case? No, it should be 1 here and 0 here. And so when you get outputs from these things, because I forced it to sum to 1, it's going to force mathematically to make it look like probabilities. But they are not real probabilities, okay? Be very careful. Because it's either dark at the bottom or it's not. This is saying, if you read this the way most people read these things, oh, it's 84% sure that it's darker at the bottom.
Can it give half and half?
What's that?
Can it give half on the top and half on the bottom?
I think there's a way to make it so that, and I did it the other day, I made one look like 54%. If they're super close, numerically, the percentages start to spread out. Like, for example, here, let me do this.
If you put the same values on the top and the same values on the bottom.
Let me do this and see what happens. Okay, if my computer explodes, the talk will be over, okay? What did it guess? Do you see that? And so, like, if you were to think of these as probabilities, you would be wrong. But because of the way it works, you could kind of think of it like that too if you want to. So you know how sometimes you run like an AI thing and then like it's guessing between like dog, cat, bird, you know, and there's like a percentage? The number comes from this softmax thing, okay? Okay, so I showed you that, and I showed you that. Any questions so far about PyTorch? Hopefully this looks very programmer friendly. Like I like PyTorch because it feels like a programmer thing that was adapted to do data sciencing. TensorFlow, very powerful, but it feels a little more like, and I know I use TensorFlow. I know how to use it. So many of you are thinking, but Seth, I thought we were going to do the numbers thing, right? We will. And we're going to do that right now. So remember how we did this top, middle, bottom thing? We want to do something like this, okay? This is what our number set looks like because we're using 28 by 28 digit pixel. If you squint and look at the matrix, what zero is that? Or sorry, what number is that? We can edit this later. What number is that, by the way, if you look at it? 0, right? This is what we actually give the computer. Remember how before we had top, middle, bottom? Now we have 10 things, right? Because this is a 7, right? Those are all the numbers. This here is a 0 and 2. What number is this? 1. This is a 0. 0, 1, 2, 3, 4. That's a 4, right? Because we're doing the same thing we did before, except now it's just we've embiggened it. Is that a word here? It's not a word in America either, FYI. By the way, remember the matrix that looked like this? Num, num, num. There's a lot more Cookie Monster stuff going on over here. Right? Now we have like a num all the way down, 783, and then out comes the 9. Right? Same thing, except now it's bigger. If we were to use another way of looking at it, right? Notice that we have, like for each one of these things, think of it as a node, right? And so this is a node, we do a dot product with all of these. Here's another node, we do a dot product with all, and it just makes some big matrix, and then out comes the 9 things, right? Turns out that if we run this, we get about, if you run it really well, you could probably get high 80% accuracy with just numbers. Just this stupid thing. On those numbers, we'll get about 80% accuracy. But it turns out that we want to be smarter about this, okay? And so we stack them. Is this a neural network? Close, right? Because it turns out that if you were to stack these linear combinations just like that, it turns out that mathematically you can prove that a linear combination of a linear combination is still a linear combination. So it's basically, if we stack them and do all the same thing, this is mathematically the same thing as doing that. So what you do have to do is you have to add a little function in between, right? And so for each of these nodes, as we go through it, we're going to do a little bit of a function. And so you know how when you do this matrix location, a vector comes out? For each one of those slots, we're going to do a function that makes it like less, like throws it out of whack. But it has to be a differentiable function so that we can do the whole thing we did before. And then this turns out to be something that looks like this. The number comes in, and in this case, I did a 512, right? We do the matrix multiply. 512 things come out. We do this ReLU function, which stands for rectified linear unit, right? And then we do it again, and then we do it again, and then we do it again, and then we softmax out, and then we get a number. This is a neural network. In PyTorch, it looks something like this, right? Which is the same thing we had before, except now remember how like I'm stacking them a little bit. And so here in the constructor, you define the things you want to store. In the forward operation, you put the things you want to execute. And then the cool thing about this is when you look at the actual graph of this, you can see that it looks something like this. But because we know PyTorch is glorious in that it will keep track of everything for us, this is just nice to know what it looks like. But it will just do it for us, right? And you can see that in this case, I think I used the same, oh, here's mean squared error, which is, I should have used something else. Everything else is the same kind of thing. Okay. Turns out that this doesn't work as well. I think this gets us into mid-90s. But one of the things, the problem that we just had is that if we take these pixels and string them out all the way across, we're losing relationships like this pixel and this pixel together. Okay? So there's this really interesting thing called filters and pooling. So I'm going to show you quickly what a filter is. So we'll take this thing and we'll multiply it by these things. So every number in here we'll do like a this times this times that. And then once we do that, we'll add the numbers all together and put it into this thing, right? Now, if you want the pictures to be the same size, you do this padding thing. And then, again, we do the same thing. We take that, we multiply it. We do dot product with this, dot product with that, dot product with that, and then we put it here. You're probably wondering, well, what the heck does that even do? Well, here's another thing we do. We can actually take this picture, and we can make it smaller by, oh, wrong one. Taking this and then take the max, oh, geez, I keep pushing the wrong, take the max value and do that. You're probably wondering, well, what the heck does this do? What does this do for pictures? I'll show you what it does for pictures. So what I'm going to do is I built this here real quick to show you what this does to pictures. So this is the convolution thing that I just did, but it looks, I used NumPy. This is the pooling thing. And what I'm going to do is I'm going to load up, by the way, here's that one thing. Remember the ones or the minus ones that we invented a long time ago? We're going to use that. And what I'm going to do is I'm going to load up a picture that's kind of important to me, you know, the wedding. And I'm going to run a convolution over that puppy. Look what this does. That's nuts, right? That ones and zeros and minus ones, if we go like over the picture, it does this. What did it find? It found edges. When we pull it, look what it does. It highlights them. Here, let me get obviously another picture that's important to me here of the kids. Same thing. Same thing. Now those are obviously supposed to be funny, but if I do like a real picture of like something that's a fence, look what this does. It's ridiculous. You see how it found all of the edges and then it accentuated them? So because of this, there's actually a neural network that does something interesting, right? What it does is it takes this picture of the number and it does filters over the numbers, and then it reduces them, and it does this twice. And then it does the regular neural network thing. So your question might be, well, how does it know what filters to use? Well, because this operation is basically a dot product, you can find the appropriate filters by doing the calculus thing. And so what it will do is this neural network will find a way to separate the picture into the right things. Just like when we look at a picture, we look at edges and colors and stuff. It will separate the picture on its own into what it needs in order to solve this number thing. And this, if you do it right, gets you 99% accuracy. That's nuts, right? That it learns how to look at a picture by filtering across it. Okay. So basically, I ran this thing with the numbers, and because I don't have a lot of time, I want to show you like what it actually outputs. Okay, and this is C#. This is the model that it This is the model that it actually learned. Let me load it up so you can see it. By the way, when you output things, you can when you save this model, it will save it into I saved it into a format called Onyx. And you can see that the input here is 0. And you can see that it actually learned like a bunch of numbers, right? So let's see if I can find some numbers. So let's see. There's the strides. No. Oh, shoot. Where are the numbers? Here's the W's for the convolutions. These are the convolutions it learned. So when you're looking at this, save file, once you're done with the training process, you actually just save the model. It basically saves a bag of numbers in a network. That's all it's doing. And the cool thing about this is you can actually load this up into a program. So I'm going to load this model here on the desktop called superfile.onyx. And then I'm going to draw a number here. So we're going to draw the number 3, and it's going to recognize it. So remember how I did that loop before? Basically, swap out the model with the convolutional neural network, run it, save it. And that's what it is. You're probably wondering, well, how did you do this? By the way, this is WinForms. I want to let you know, like I went all the way down. And you're probably wondering, well, how does one do this in WinForms? Well, the first thing you do is you need to load up the actual file. And because we have this thing called the Onyx runtime, you can just load up an inference thing. The next thing you need to do is we need to convert what I just drew into the thing that it expected, which is 28 by 28. And you can see here I'm just pulling all the pixels out and making it a 28 by 28 pixel picture. And the last thing I need to do is I actually need to predict. Let me move this here because it's like in the way. And this is how you do it. You create a, remember how the input was 0? The 0 input? I pass in the x. And then from the session I loaded, I run it. And then the output comes out. You can see that because I made it an array, right? This is the array, and I'm getting the max value out, and that's the prediction we make. And so now if I were to write another and if I do something like this, you see why I kind of don't like when it says, well, I think it's an 8, but you know, with 28%. Do you see that? And so hopefully you've seen that this is all literally a bunch of engineering. By the way, this is what this model looks like. Because convolutions happen so often, it's part of the class. And then when you run it, it actually does that. By the way, Onyx is the Open Neural Network Exchange format. If you're a .NET programmer, if your data scientist exports this into Onyx, you can look at that file like I just did in Netron, know what comes in, know what goes out, and you can use it as if it was a function, right? That's cool. So I did that. By the way, this is the Onyx runtime. It's a NuGet package. You can download it right now, which is really cool. The last thing I want to talk about is this stuff takes a lot of time. We have something called Azure Machine Learning Service, which actually lets you do all of this stuff in the cloud and share it with your friends in your workspace. All right. That's the cool thing. It lets you run a bunch of experiments. I forgot I even put this slide. So this is me running all this stuff, but in the cloud, and how long it takes. All right, so just a little summary because I feel like I'm out of time. We learned some deep learning principles. We talked about the input. We looked at the model function, W transpose X plus V. B, we looked at the cost function, right, which is a mean squared error, H of X minus Y squared, mean. And then we looked at the optimization method, which was gradient descent, right? I also motivated the fact that atom optimizers, which are better, are just a variant of gradient descents. In PyTorch, we looked at tensors. We saw why they were special, because in this case, they keep track of gradients for you. We looked at datasets, how to load data, and we looked at data loaders that actually aggregate these things together. We also looked at how to build models in PyTorch. We looked at the losses, because these are all classes, and then we looked at optimizations. There's a number of different optimizers. I showed you mean squared error and atom. And then finally, I showed you that inference was basically getting that model with the trained values and just executing it and getting a prediction. We also looked at Onyx and Azure Machine Learning Service. If you want to learn more about this stuff, feel free to do that. All this code and these notebooks are available online at this GitHub address, Deep Learning with PyTorch. You can run them all yourself and see it, because I feel like I went really fast and I literally covered 5 weeks of grad school plus a workshop on PyTorch in an hour. So I feel like it was really fast. So if you feel like you did not get all of this, hopefully you feel like I am comfortable enough to know where to look and how to start, and I know what's in it, and I know how to use it. That was the goal today. Any questions? Thank you so much for your time. If you have questions, you can ask it.
You were very keen to the Irish of the